All right, let's get started. Thanks for watching. I am Matt Taylor from Dementa. This is, I think, this is only the second AI chat that we've done. I did one last week, yeah. So this is only the second AI neuroscience chat that I have done, and I even have a little chat command for it, AI chat, and I just kind of described what it is. Today we're going to be talking about pooling. And before I start talking about pooling, does anybody have any idea what pooling is at all? There's a way to describe it, I guess, in deep learning. I only know of one way of describing it in deep learning, and I'll show you what I'm talking about here on the screen. So this is the deep learning idea of pooling that I understand, and that is you have an input space. I like to call these input spaces. These really represent neurons in if you're trying to relate deep learning to neuroscience. These bits really represent either neurons or synapses to another neuron, So the pooling sucks. Why does pooling suck? I guess I don't understand that. I've never heard anyone say pooling sucks. It's sort of pretty cool when you understand what it's doing. It's like it's a cool trick that your brain is doing to take information in one space and translate it into another space, sort of. So that's what I'm going to be talking about. The type of pooling that this is showing is doing the same thing, but it's losing a lot of information. Yeah, I guess that's your point, right? It loses a ton of information. So when you pool, especially using max pool, okay, so in this example, each one of these, we're basically taking an input space and then breaking it up into separate spaces that will then be represented by another unit, right? So you're sort of adding another layer of units after the convolution to further decrease the feature, squelch down the feature space. And in this case, I think this is probably showing an example of maximum pooling, which is you basically look in that space and you take the max value, the unit with the maximum value, right? And that's the one that's represented. But if you think about this, you could do this in lots of different ways. You could apply any function over that space and transform a whole bunch of units into one unit, right? That's pooling. You could do max pooling, min pooling, mean pooling. You could apply lots of different mathematical functions as a part of this pooling. So it's an interesting concept, and it's similar, I think. This sort of evolved. This sort of came from biology, but in biology it works even more differently than this, I would say. So we're going to talk about first. Let's think about what a pool is. Okay, so we call it pooling for a reason. If you're pooling, let's draw a pool, right? Let's draw a stream of water into a pool, right? So we've got a stream. It's important that you think of this as a stream, I think. I should have used blue for this, but I don't think it really matters. But this stream is, the stream implies, like, if you sample this, if you take all the water molecules right here and sample them out, you'd have a state, in that stream. And anyway, what the pool is doing is it gives you an opportunity to take the data in the stream and organize it somehow, map it in a different way. So here's the way I would draw it, and you can have lots of pools. There could be a pool up here, and then another stream leading into that. There could be a pooling here. It could be pooling here. It could be another stream, another pool, and each one of these pools might mean something or represent something different, depending on how has been mapped onto the stream, sort of like the space that's being pulled into it. You might see this space. I like to call this, if you're talking about a layer of neurons, you could think about this in a deep learning manner as well. You could say a deep learning layer or a cortical layer. Let's just say a layer is a bunch of neurons that are all working together, a population of neurons. These neurons map, I mean, they have input, right? These neurons will have input, and typically the input can be expressed because sensory input is typically topological, so the input can be expressed as some type of topological space. So this is some topological space, and it's really similar to the convoluted feature. That's also a topological space, right? So in this topological space, what we're doing differently is we're not going to say this group of this one neuron. Let's just say there's one neuron here. I'm not going to say you're connected to 1/4 of it, and or this little portion, you're connected to that little portion. We're going to do it differently. That's a start. That's a start. So what we're going to do, and this is what biology tends to do, is each one of these, say we've got each neuron. For simplicity's sake, I'm just going to use one example of a neuron here. Each neuron has a potential pool of inputs that it might be connected to. In deep learning networks, typically you have dense connections between a unit in one layer and the units in the layer previous to it. Hi, Akela, 51. It's your first time here. I'm talking about neuroscience and AI, specifically pooling, and I'm sort of relating the max pool idea in convolutional neural networks and to how it really works sort of in the brain. And so I'm talking about a population of neurons in the cortex getting sensory input or input, proximal feed-forward input. The important thing, this is going to be input. Every cell in here is going to get input into this from this space, and this is feed-forward. Feed-forward typically means in the direction of the senses. So like information flows from your senses up through your brain. And when you say feed forward, that means that's the direction it's coming from the senses. So the difference here between something like this convolution pooling that we're doing here, there still is information being lost. Just like anytime you pool, you lose information. So the trick is to lose the right information, or lose the information that's not necessary when you're learning something, right? So what neurons typically do is, and neurons grow, right? They grow from one point to another point. And hold on a sec. So there's not like they're not connected to all of them. There's some potential amount of connections that these cells dendrites are close enough to the other cells dendrites to make synapses, right, or axons. And it's actually these axons growing up into, I think, the dendritic branches of these neurons. So we're talking about axons from this layer and dendrites from this layer, I believe. But the point is, you can't possibly connect to all of them. So the idea of dense connections. Hey, thanks for the follow, Akela 51. I appreciate it. I'll be doing this stuff every week. So this is like my new job, explaining how we believe the brain works, and that when I say we, my company, Numenta, pays me to do this. So we're trying to understand how the brain works in the neocortex and the thalamus. We're trying to understand the common cortical circuit in the neocortex, which involves the thalamus. And anyway, I'm talking about pooling because pooling is like a crucial concept. You have to understand spatial pooling. So I'm going to get to spatial pool. This is what I'm basically describing as spatial pooling here. And in spatial pooling, this would be a mini column, which is a column of a small column. This is not a macro column, not a cortical column, but a small column of pyramidal neurons that all share the same receptive field, the same basically potential pool of connections that they could always have. You joined our community. Did you join the HTM forum? That's the best place to join right there. That's a very active. We've got a very active community of people there. So you're welcome to come and ask questions. Stupid questions are fine. And if you have a question here, I'm happy to take it. That's why I do these AI chats. I just want to engage the community, give you guys a chance to ask me questions live, and I'll keep doing it on Mondays at 1. Pyramidal, let me spell that out for you. It is like a pyramid, pyramidal like this. So a pyramidal neuron is what is typically pyramidal cells. Pyramidal cells, pyramidal neurons. These are typically what we think does most of the hardcore computation, I guess, of the brain. Here's sort of what one looks like. So there's inhibitory neurons and there's pyramidal neurons. And pyramidal neurons, I believe, are never inhibitory. They're always excitatory neurons. Yeah. Okay. I see you explained advanced knowledge. I guess I don't know I don't know where I'm going to try and meet you guys wherever you're at. So I'm happy to step back. Step back and explain some things. But I'm talking about our model of pyramidal neurons. However, I mean, I'm talking also about mini-column, and we believe these mini-column structures are most likely enforced by inhibitory neurons that activate in the same layers as the pyramidal neurons. So, I mean, there's a lot more than just pyramidal neurons going on in your brain. If you took out everything but pyramidal neurons, your brain wouldn't work. But we're focusing on modeling the pyramidal cells, like you see here, with the effects of all the inhibitory cells too. So, I mean, we need to model the whole brain, but for the most part, these are the ones that seem to be holding the computations or like holding memory, while the inhibitory neurons perhaps enforce a structure so that they can compute within. Okay, so I'm trying to explain pooling. So the tricky thing here is it's super easy when I think it's a lot easier when you think about the convolution, because it's really simple to think, oh, I've got this unit and it just maps onto this block of the input. In this model, let me try and erase this a little. If we're still, we'll say this is an input space. Okay. Blah, 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 blah. So one of these mini columns that I have drawn in blue here, one of these might project, and this is just my speculation, it projects topologically onto the space. So it's not going to project across the whole space. There's usually a localized inhibition happening here. So this mini column is sort of competing with its neighbors in its network right up here about which one is going to represent the activations here. So you have to also remember that in this space, there's neurons firing too. So at every time step, this isn't a very good example, graphic here, but every time step, let me go back to the whiteboard, sorry. Every time step, we're seeing an activation pattern in this input space, just similar to you would see an activation pattern over here in the convolved feature. You'll see an activation pattern in this input space. But each of the mini columns are going to have a localized connections, and we call this local inhibition, where you might have a mini column over here that projects into this space, a mini column over here that's receptive field is in this space, but we're breaking it up in a way that we don't have to, like if you look at the convolved feature, we don't have to have less space. We can make this structure as big as we want. So one of the ideas of spatial pooling is to change the representation here, transform this representation using these mini columns, receptive fields, so that the mini columns will start to represent things in here. And like I said, this is not a dense connection. It's not going to connect to every single. It will never connect to all of these neurons in here. It only connects to a percentage of them, because that's the way it works in biology. I mean, this mini column will never have the opportunity to connect to all these neurons because they're too far away. I mean, it just doesn't happen like that in your brain. So all of these mini columns are essentially pooling features, pooling things that they see in here, and representing them when they see that thing occurring. So if you look at this, we can sort of randomly set up these initial connections, right, from one mini column to an input space. And if we just randomly set them up so there's a potential pool, and we just randomly set the weights of the connections around some Gaussian distribution so that they're almost connected, then as soon as we start streaming information, remember I said stream, that's super important, stream. That's another difference I'm going to point out here. As soon as we start streaming information through this, it's going to be spatial information by nature, but the fact that one point comes after the other is super important. That's the temporal nature of the world. You have to think of this as a sensory array, not necessarily just an image that we're looking at as a part of a million other images that we're trying to classify. That's not how your brain works. That's how deep learning networks work, yes. That's not how your brain works. Your brain is expecting each image that comes, or each whatever it is, each sensory array, to logically follow the next. There's a reason this activation comes next. There's a reason the next activation comes next. It may be because you're moving the sensor through space. It may be because an object is moving against the sensor in space. You know what I mean? So what you end up having here is you get a set of activations in your input space, and you will get a set of mini columns that activate here. Let's say there's another one. And because of these activations that occurred, we have another set of activations in this other layer, in this population of cells, that now represents this data. So we've transformed the data out of this space and into another space. And in this space, one of the important things is we can control how dense this representation is, how many columns win this competition, because there's sort of a game happening up here, and it's all localized. There's this localized game, so all of the mini columns that sort of are looking at this space are competing to decide which one has the most overlap with the semantics within that meaning, and that's the one that's going to win and fire and represent that pattern from here on out. And we can learn that over time. If we all of these weights, because these are all weights here, all of these weights will be updated as different columns start tuning to the spatial input that they see. So these weights will learn. By changing these weights, this population of neurons learns to tune to the spatial patterns that continuously stream across this input space. Have I lost anybody? Does that all make sense? I'll take questions. I'm happy to take questions. This is sort of like the basics of how a spatial pooler in neurons, and we have simulations of all this. This is like tried and true, software tested. We've got this all in software. It works totally. And what this gives you is a way to represent semantic. This is sort of like how information gets encoded from your senses into your brain in a way. Like you've got a certain encoding coming out of your senses, out of your retina, out of the nerve, optic nerve, auditory nerves, coming into your brain, into your thalamus. And once it gets up into cortex, we have to translate. It has to transform to be represented in cortex, because the cortex, the neocortex, is where you're modeling objects based on this sensory input. And so this is sort of the first step of modeling those objects, is taking the sensory input and transforming it into sort of a dimension that the brain can control, if that makes sense. Let's see. So this is spatial pooling. And there's more to it than this. There's boosting, which I'm not going to talk about. Well, yeah, I will talk about that. So one of the problems that we face by applying spatial pooling in this way, and it's a problem your brain has found a solution for, is, I wouldn't call it, it's a little similar, I guess you could say. It's similar in concept to overfitting, if you understand that concept, but what quickly happens if you set this up without something to enforce entropy in this space, that certain mini columns or certain cell activations up here just sort of lock in, and they start representing too many patterns down here. So you'll get a small percentage of cells up here representing a large percentage of the different patterns that come across this space. So one way, or the way the brain seems to fix this problem is called homeostatic equal. Well, basically, it's homeostasis in neurons. How do you say it? It's some type. There's a phrase that's homeostatic plasticity. I think this is it. The capacity of neurons to regulate their own excitability, yeah, relative to network activity. So this idea of spreading out the meaning, okay, is something that that the brain seems to do, and there's papers about this and mechanisms of doing it. So our mechanism we call boosting, and it's like an implementation in software based on this spatial pooling implementation in software of how to prevent that from happening, right? Prevent a few mini columns from representing way too much data or patterns down here. What sort of activation function? And this, okay, so when you're talking about activation functions, we call this, or if you're going to look it up, you would look for like K-winners or winner-take-all K-winners or something. That's the equivalent activation function that you would use in a deep learning network. Because essentially, you might have 1,000, 2,000 mini columns up here, and in response to this, here's what you do. There's a great, I say great, but that's little. There's a great HTM school about spatial pooling, if I could spell it right. So there's, go to the one, episode 7 talks about this mapping to the input space, and episode 8 talks about learning. So in episode 7, at the end of it, it'll talk about, I don't even talk about boosting in that, do I? There's a whole other episode about boosting. I think that's episode 9. And in episode 9, that's what it is, I think.
Brains.
Hey, Viz, I don't know how to say your name, but thanks for the follow. I appreciate it. Talking about brains. If you like brains, you're in the right place. I was just talking about our implementation of homeostatic plasticity in our HTM theory, which we call boosting. Okay, so let me just tell you how boosting works. Instead of, so usually what happens is, in response to some stimulus, some activation pattern in the input field, you've got, all these thousands of mini columns, and we'll stack rank them based on their receptive field. They've got a certain amount of connections open over here, right? And their overlap with the bits in the space that they're covering, right? So they're trying to pattern match in the space, saying and looking for a lot of activations in their receptive field. And so you might get one that's got, I've got this column has 40 overlap, this one has 38, this one has 38 too, this one has 37, and we'll stack rank them. All of these columns, we'll rank them, rank by overlap. And that is the overlap of its potential connections, its receptive field of synapses that have already been established, right? Connected synapses to the input coming across those synapses. And what we'll do is we'll stack rank them, and then we'll draw a line. We'll say I only want K winners to represent this input, and that's what we call K winners. And that is inhibition. this in HTM theory, we call this inhibition. Inhibition, I'm expressing this as a local function. So there's local inhibition. So there's groups. Each mini column has a neighborhood of columns that it's competing with, and getting stack ranked up against, right? Because that's what you need if you have topological input. But a lot of times you don't have topological input. If you're just looking at scalar data, for example, which is a big use case, temporal streams of scalar data. If you just look at a server and its metrics over time, that's all temporal streams of scalar data. BTAS, thanks for following. I appreciate it. Awesome. I'm glad you guys are enjoying this content. So I'm talking about local inhibition, but there's also global inhibition. And just imagine that in global inhibition, the potential pools of each mini column spread across the entire input space. So basically there's one neighborhood. All of the mini columns are competing with each other every time. That's global inhibition, and that's much more efficient. I mean, if you think about it, the more neighborhoods and the more competitions you have to compute. Your brain's doing this in parallel constantly, but in the CPU, there's the more localized the inhibition occurs, the more computation occurs, like exponentially more computation occurs. Okay. And like I said, if you want to see that, go to that HTM school link, and there's a video about boosting there. What will happen if the input is empty? Nothing will fire. Like these cells up in this layer that we're simulating will only fire in response to activations in the input space. If there's nothing there, they don't do anything. It's like nothing happens. Compute stops. I mean, there's nothing to do. And in the real world, that doesn't exist. There's always something. If you're awake, you're receiving data. Even if nothing's going on around you, you still have sensation, right? You can still feel. Like, close your eyes, I can feel where my hands are. Like, I still have sensors that are giving me input constantly. So you have to think about this as a stream over time. This is not just a spatial classification task that we're talking about. When we're talking about HTM tech, hierarchical temporal memory, we're talking about a stream of temporal data flowing across this input space, and this responding and learning to it in real time. Online learning, completely online learning. This is something that deep learning networks cannot do today. So this is the idea of spatial pooling. So we're taking features essentially, and we're going to start representing them differently up here. And once we can represent them differently, and once we've applied, I forgot to explain boosting. I'm still trying to explain boosting. Okay, so I explained the K-winners and the local inhibition, the competition that occurs to decide which winner mini columns are going to represent this data down here. And I also said that if we let it go willy-nilly and we don't control and we don't enforce entropy at all, then a small percentage of these mini columns will start representing a large percentage of the spatial patterns that come across. And that's why I was talking about homeostatic plasticity, because your brain solves this in a certain way, and we're trying to do it in software a similar way. So what we do, and this is a little compute heavy, right? But you have to keep a duty cycle for each one of these mini columns in here. So essentially, for every mini column, if you have, we typically 2048, we'll say 2048 mini columns is a typical size of an HTM network that we'll create and do and build experiments on. BTAS says, doesn't drop block perform spatial pooling? Drop block. I don't know what drop block is, sorry. So I'm not sure. And by the way, spatial pooling may be a bit of an overloaded term. These are both general terms, spatial and pooling. So drop block might be spatial dropout. I don't know what spatial dropout is either. As far as I know, this concept of spatial pooling is a unique discovery that's a part of the HTM canon. I've never seen anyone else doing something like this. Spatial dropout, that might be a technique that's used in deep learning networks to try and sparsify the network, because deep learning folks have recognized that sparsity helps. It helps especially against noise. So there may be a tactic called spatial dropouters, but I'm not familiar with it. So anyway, to apply boosting, you have to keep an active duty cycle for each one of these columns. And an active duty cycle is just, imagine a time window. Say I'm going to look at this one column, this one mini column over time. So you'll just keep a little counter, and you'll say, for the last 100 time steps, how active has this column been? That's basically it. You're just going to check, is it active now, and then add it and tally it up and give an indication. We call this ADP or ADC, active duty cycles. So we're going to keep an active duty cycle for each one of these, and the boosting step will then do a computation based on all of the active duty cycles and come up with a boost. We call it a boost factor. Boost factors, one for each column, and just multiply that column's. I'm not exactly sure how it does this in the code, but it's simpler. It's pretty much what I'm explaining. It's you just look across the active duty cycles because you want to prevent some of the columns from being too active. So you'll prevent the columns that have been very active from representing new input, and you'll pass off that semantic meaning to another column that has not been active. So you're basically just keeping, because like I said, otherwise you'll get, because you can represent a lot of information in one of these mini columns. It can represent a lot of spatial input, a lot of spatial patterns. And you'll get a situation where you've got just a few of them representing a lot of spatial patterns, and you don't want that, because you want to enforce entropy in this layer so that you can spread the meaning out through all of those mini columns. Mark Brown is in, the king. Good to see you, Mark. I was just talking about boosting, homeostatic plasticity. So we were talking about pooling. I talked about local inhibition. I talked about mini columns and how they map to input space. We talked about K-winners. We talked about active duty cycles, boost factors. So if there's any other topics you want to talk about, I'm going to go on to the idea of temporal pooling or object pooling next. But one of the key concepts that you really have to understand that's different from deep learning, if you're coming from the machine learning or deep learning world, I keep hitting on this again and again, it's that this is a stream of data. It's a stream of data. If you look at this, there's a constant stream. It's constantly changing. And your cortical layers are observing that stream of data over time. It doesn't make sense without time. I haven't talked about bursting yet, because that's sort of a part of the temporal memory system. We'll talk about bursting at some point. The topic is pooling. I don't mind talking about bursting, but it might get a little bit too far ahead too fast because I haven't explained temporal memory at all. Bursting is sort of a key part, but the interesting thing is that I like explaining bursting, so I'll give you a little teaser. If a pattern comes across here, so every step, there are cells in these mini columns that are predicting what they're going to see next. Okay, that's the idea of temporal memory, which we haven't touched on yet. But there's going to be cells that are active up here, like right here, and that means they're not trying to represent what's here. They're representing, based on everything they've seen in this space, what do they think is going to happen next? What pattern is coming next, right? So if it's wrong, if this cell is wrong and you get the next input step and there's a totally different input that comes across here, a really interesting thing happens. Every cell in the column then turns on. And you see this in the brain. This is called, I don't know if they call it bursting in the brain or not, but you see this in the brain. It's sort of like surprise, almost. It's like something happened. Yeah, surprise, Mark says. It's so cool because you can see, more neurons activating in your brain. When something shocks you, your brain's kind of like, pop, like what? what the hell was that, right? What was that? And it sort of, it makes sense in a way because you don't understand what's going on, and you activate all of these cells to tell it any number of things could happen. Any number of things could be happening right now. The possibilities are many, right? And as that pattern replays itself, it locks in to one of these neurons that will decide to represent that pattern over time, as you see it over and over. And then the next time you see it, that's the cell that will predict, right? That's how you learn. That's how you create memories. Well, one of the ways in which you learn. It's a key. It's a really crucial part of how you learn, honestly. I don't know how you could learn without a mechanism like this in some way that takes like sensory information over time that's constantly flowing into your mind, into your brain, specifically through your thalamus, into your neocortex, and trying to understand what's happening all the time. And if something unusual happens, like a bunny pops up in front of me, all my mini columns are going to burst because that's never happened before. That wasn't what I was predicting. Now I have to come up with some new explanation for this reality in front of me that seemed impossible a moment ago, right? That's bursting. Say the bursting mechanism. Let's talk about bursting in another AI chat. That's a good topic for another AI chat. Yeah, I think it will have something. So the tonic, you're gonna love. I got to get this podcast edited, Mark, because I talked about tonic and burst modes with Subutai, and now I can't remember all the details about it, but it's important for sure. Okay, we're gonna go on to a different type of pooling. So assuming that we understand this idea of spatial pooling, then we can assume, let's assume again, we have a layer of cells, a layer of neurons, and again, let's assume there's an input, there's sensory input coming up to this, proximal, feed forward, sensory input, right? So in response to that, you'll have some mini columns that get activated in here. This is the way I typically draw them. And there will be cells, and we haven't done temporal memory yet, but there will be cells in here that are active, and those represent sort of the context of that spatial input. We'll talk about that when we talk about temporal memory. How is information returned back? So that's a tricky question. How is it returned back? Returned back to what? We're talking about feed forward. Are you talking about feedback to, because this sort of flows, information flows from sensory through your brain up, essentially through the hierarchy, and motion information emits out of this. So I haven't really talked about this, but every single cortical column in your brain outputs a motion signal, a movement signal, which flummoxed scientists for a long time. Because why would you need that in every single part of your neocortex? But it does. It seems like in every part of your neocortex, including your ears, your eyes, all of that is creating some motion signals. So you're sort of constantly putting together a motion pattern for your whole body all the time, right? So there's always this constant output, and it's not coming from this particular layer. It's coming from a different layer that but let's ignore that for a moment. I'm not talking about backpropagation. I hope you're not, DeFrokill. There is no backpropagation as far as we know in the brain. And one of the problems with backpropagation is it's sort of this, it's like you have to have access to so much information in a global way to run that algorithm and do that error correction we don't see that there is the connectivity, I think, to do that. It's probably done through apical credit assignment, and that's what I think. But anyway, I'm getting off topic. If you just saw the bunny for the first time, you pool it, but you can draw later if you want. Oh, you mean if you've never seen a bunny before? So I think you would probably, so here's the thing. You haven't seen a bunny before, right? But you've seen rodents before, you've seen furry things before, maybe you've seen mammals before. So I mean, even if you saw a bunny, you've never seen one before, you'd immediately know some things that were similar to it, right? That's crucial. That's because that bunny that you saw with your sensory input has semantic overlap with other objects that you've already learned in your neocortex. So even without learning it before, you can already relate to it. You can already relate to it, and you can compare it to things that you already have representations for in your brain. So yes, there would be bursting. There'd be bursting because it's out of context. You've never seen a rodent appear in front of you on your desk or whatever before. And also that one looks a little odd. And you've never seen a rodent that looks like that with long ears and a little bitty button tail, right? But that's something you would have to learn, and you'd have to inspect it. You know, you'd have to look at it. And if you just had like a flash of it and you weren't able to inspect it, like explore it, and because all of our intelligence, I believe, is based on the exploration of space and using your sensory input in coordination with your movements to explore space. You have to know how you move through space and how the objects respond to your movements in space. Anyway, I think I'm getting off topic, but that's okay. It's AI chat, so we can get off topic if we want to. But I want to talk about another type of pooling. So this is a little bit of a trickier type of pooling because I'm jumping ahead. I'm going to talk about this idea of temporal pooling, and we haven't really talked about temporal memory yet. So I think the easier way to think about this is to talk about object pooling. And this is one of the key ideas here is this circuitry that we have in our cortical column. So not only do you have this layer, you have another layer, you have another layer. There are something like 10, 12 different layers depending on who you ask. I think there's 6 like easily differentiable layers in your neocortex, but then there's multiple different cell types in many of the layers, and so each one of those could be said to be doing something different, and maybe you can treat that itself, each different cell type in a layer, as a different layer itself, since they have different compute. I mean, there's even going to be layers down here, and as proximal input feeds into this thing that's doing spatial pooling, at the same time, it's doing another process that we call temporal memory. I'm not going to explain that right now, but essentially it activates different cells in each mini-column depending on the context over time that it's receiving the input. So essentially it's storing sequences of spatial patterns. So you can, using this mechanism that I'll explain in another AI chat probably, you can identify, or you can make predictions. That's the key thing. You can make predictions about what you think is coming next, and the predictions will be in the context of all the other sequences that you've ever seen. But the hard thing here is that you don't know what the sequences are. That's the tricky thing. You have the predictions, but in order to dive into this layer and identify all the different sequences that this particular activation might right now be playing out based on your experience is particularly hard. Let's see, I missed a chat here. Is explainable AI possible with HTMs? Also, how would it go about explaining decisions being made? Okay, so I'll take that question. Explainable, so definitely, I would think it's possible, definitely. And in fact, I don't think that that's like our mission. Our mission is to understand how intelligence works in the neocortex, in the brain, essentially. So how much more explainable can it get? That's our mission, is to explain AI, explain intelligence, so that we can make intelligence. That's crucial. So absolutely, it's explainable. That being said, there's this idea of reality, and we haven't talked about this. I don't think I love bringing this up because it really hit me when I read it. So I read a book by Max Tegmark. Actually, Jeff Hawkins suggested it, so I read it. And it was called Our Mathematical Universe, something like that. And he has this idea of 3 different realities, and this totally hits home for me. When you're talking about AI, this is a great way to think about it. You've got 3 different realities. First of all, there's like true reality. There's the reality, external reality, he calls it. There's the reality that's out there, and it's everybody observes it. Everybody has a window to that reality, but nobody has a complete view of that reality, right? Now, then there is internal reality. So I have my own internal reality. It's represented in my brain. You have your internal reality. It's represented in your brain. There is no way for me to completely share my internal reality with you. The way we do this is through a third type of reality that Max Tegmark calls consensus reality. That's the reality that we're both existing in right now. It's the reality in which I'm speaking words to you and you're understanding those words or trying to understand those words and making an internal representation of them as you're trying to understand these concepts. So I have this internal reality that I'm trying to project through the consensus reality, through education and through this Twitch channel, for example, so that all of you can update your internal realities to have a better understanding of my internal reality, right? Does that make sense? So think about AI now, because there's no way that my internal reality could be interpreted by you. There's no way, unless you took my head off and put it on your neck. And in that case, who are you anymore, right? There's no way I could freeze all the neurons in my brain. I could map them all out. I could put them all in a computer. There's no way you could make sense of that. There's no way anything could make sense of that except me, period. And you know why? Because all those representations are based on my body. They're based on all of my experiences I've ever had. As I did this interview with a neuroscientist, I've done too many of these. Michael, I follow him on Twitter, I'm sorry. He's a motor guy. He does motor inference stuff. And I asked him, what is it? Somebody jog my memory if you can. It's on my YouTube channel. It's on the YouTube channel under Interview with a Neuroscientist. I asked him, what happens in your brain when you go reach for a cup, right? What happens in your brain when you reach for a cup? What is activating? And he's like, well, it's like the sum experience of every time you've ever reached for a cup or ever done anything with your hand comes into play when you do that. Like, there is no separating the way I reach for a cup from me, from my identity. That internal reality cannot be separated from my experience. Right? You can never understand if my interpretation of red is also your interpretation of red. That's the idea. So with AI, you're going to have the same problem. If we're creating intelligence that's based off of how our brain works, even if we can explain all the minutia of the cells and the layers and what's happening here, you're never going to be able to take an internal representation inside of a common critical circuit that's down here that's related specifically to the sensory input of this agent and its experience with reality. You will never be able to compare that with anything else and make sense of it. Does that make sense? Now, that being said, we can create some really elaborate consensus realities so that we can communicate with these AIs once we get to that point. But you can never expect to look into these cell activations that I'm drawing up here and expect to know exactly what experience that agent, that entity, that intelligent thing is experiencing. Jonathan Michaels, thank you, Falco, that was him. Jonathan Michaels, if you're interested, I thought this was I really liked this. Let me look it up real quick. Jonathan Michaels, he's on Twitter too, Interview Neuroscience. There we go. Oh, you got it. Thank you so much. Okay, so if you're interested in that idea of motion and grasping, okay, I'm going to try and catch up on chat here for a minute because I've been just talking and talking. So if you just saw mini column sequences in one map of mini column sequences in another map. Yeah, is explainable AI possible? That's where we go. You might like the next wall of text sent to predictor. Okay, that's on the HTM forum Mark's talking about. It may be explainable in its principles, Falco says, but unexplainable due to complexity. It's not complexity. It's unexplainable by nature. That's the key. You got to remember, because an intelligent agent's experience is unique to its movement through space. So as you could train. Let's assume you had an AI robot and it was smart. However, we made it smart, right? And we turned it on and we let it learn how to move around in a little room. Okay, so it's learned the room. Now you could clone that thing and send it off into a bunch of different rooms, and the rooms would be different, right? And then turn them back on and say they're all learning again, and they all keep moving through those rooms. Each one of them has now diverged from its original internal representation. You cannot compare them to each other anymore. There may be some ways that you'll compare them for a small amount of time while the overlaps are similar, the things they've learned. But as they learn new things, they're going to diverge, and you're not going to be able to reliably take that internal representation and turn it into anything meaningful over time. Okay, reality that is collective. Yeah, so that's the consensus reality. Where have I heard everything you learn is in terms of what you have learned before? I don't know, but that's absolutely true. You bring your full experience of the world to every new situation. There's no getting around it. You can't really bake it down to just here's the input. It's like everything you've ever learned is a part of your experience. Betaz says this reminds me of the Sybil system in the anime Psychopaths. I'm gonna leave you guys up to investigate that. Have you tried to build reinforcement learning HTM agent in common reinforcement environment? So that is definitely a huge deal. That's the future. Absolutely. Reinforcement learning with HTM is most certainly the future, especially in the direction towards robotics and gaming applications for HTM. That being said, and I've talked about this a little bit before in other chats too, hold on a sec. The mechanism for enabling that is not quite nailed down. So if you want to look up this paper, it's the framework paper. This sort of defines sort of this one right here defines sort of the idea of displacement cells. Okay, displacement cells. If you can. Now I always get too deep because these chats get deep fast, but you have to understand how grid cells work. You can represent different locations in space. Yeah, what he's saying, you have to have the RL system has to be learning. The HTM pooling is a whole different animal. It's true, but they both have to learn together. I think, to have something intelligent. They have to have feedback. There has to be back and forth. There has to be some type of integration. The key thing, I think, is that the HTM system plays a part in creating movement, right? Like I had a little arrow over here. The HTM system has to play a part in the causation of movement. In that way, it has to understand how its movements affect the sensory input that it gets back. And I think the way that it has to do that is by having some representation of displacements between locations somehow in one of these layers, so that it knows the repercussions of its movement, because it knows where its sensor is. If it's a part of a movement, it has to predict where it's going to be next, and then what it's going to feel when it gets there, and that is a part of the feedback that comes back as sensory input. And we're not quite sure how these displacement layers play with the other layers that we've identified. But once we figure that out, I think the link to reinforcement learning is like right there. That's the point, where you take the action in the environment, and you have some type of goal reward set up there in the lizard brain, as Mark Brown likes to call it. Right? I hope you're agreeing with me, Mark, here. So that we can attach our neocortical model of the world to that control center, that control system somehow. So that's sort of the idea, and the reinforcement learning system would be more of a model of the older part of the brain, that's dealing with reward and punishment and stuff, but at the same time, it's constantly keeping a link to the models that it's attending to and exploring, etc. And make no doubt about it, I feel like we're talking about thalamus and neocortex here. I think that's the huge link, and that's the direction we're headed. That's definitely the direction we're headed. We haven't gotten to a point where we're ready to create any type of reinforcement learning system yet, but we've got some toes in the water for sure. Also, the way that the amygdala assaults the memories that are forming. Yeah, that's a good way to put it. Seasoning the memories. The emotions are a part of this for sure, and I think emotions get represented all across your neocortex. I think they're a part of every experience that you have. Your emotional state when you learn something can affect the meaning of that, absolutely. And I think that that spreads through your whole brain. Yeah, it's definitely it's a way that the lizard brain projects to the cortex. Your fear response, your fight or flight response. If you see an object that invokes fear, that's evidence right there that the emotion is stored right there with the object representation, right? That makes total sense to me. I haven't even gotten to object pooling yet. I'm thinking maybe since we've already reached like an hour, I'm wondering if we should talk about temporal memory instead of object pooling, because I think I'm going to have a hard time explaining object pooling without explaining temporal memory. Are you guys still into this? I could keep doing this, but I'm gonna have to take a break. So why don't you give me 5 minutes, and I will come back, and we will have a little break, and we'll talk about temporal memory. I haven't prepared anything on this, so it's just going to be sort of off the cuff. But Film Tire, you're too kind. Thank you so much. That's awesome. I'm glad you guys are enjoying this. I think this Twitch thing is just amazing. I'm very excited about it. It feels like I'm the only person consistently creating any like AI neuroscience related content right now on Twitch, and that's a great place to be because I feel like this platform is really blossoming right now. There's a lot of things going on in the science and technology game in Twitch, if you know what I mean. All right, guys, I'll put a little music on for you, and I'm gonna go to the Be Right Back screen. So I have more viewers now than I did before I took a break. Let me turn this down. I feel like I'm on Twitch, so I can be just like whatever. I can just do whatever I want. So I'm gonna wear shades. Better turn this off though. We're gonna talk about temporal memory. I'll leave it on real low. If it bothers anybody, let me know. I'm gonna draw something different than this to explain temporal memory. You guys all with me? Everybody still there? Brain hurts. The music's out of key. I didn't notice. All my whiteboard things are gone. Let's see. Reset. Okay. All right. Now it's okay. That's weird. All right. It doesn't matter, right? So let's talk about this input space again. No, let's talk about a mini column. Here's a mini column. All right. This is in some layer of cortex. So there's lots and lots of mini columns. So we're just going to talk about this one mini column. And I think we would typically say we see this behavior in layer 2, 3, and I always forget it. I'll talk about cortical layers another time, and I'll have done my homework by then. So let's just say this isn't happening every single layer of cells in the neocortex, but I think it's crucial at least 2 of them. So each one of these mini columns represents a bunch of cells, pyramidal cells. So let's say a mini column has many, I'm just going to call them cells. And when I say cells, you can just think of that as a pyramidal neuron. Let me make sure, okay. So like I said before, I like to draw the input space in green. We have some input, and it's just a big grid of cells as well, which it's also you can sort of see these as synapses or cells that are in either a lower layer, another layer. This could be another layer. It could be another layer, or it could be sensory input, like direct from the thalamus, or that's relayed through the thalamus. Or perhaps there's even olfactory goes straight into your cortex, so maybe direct sensory, maybe through the thalamus. The point is, this layer doesn't care. It doesn't know. It doesn't care. It doesn't know what it doesn't know. That's one of the things that makes it common, a common cortical circuit. We're looking for something that can be generalized, that generalizes everything, right? That's why we're so smart, because we can generalize so much stuff. So we've got this this mini column forces all of the pyramidal cells within it to have the same receptive field to the input space. Okay, so assuming that it has some receptive field to the input space, and it activates in response to cells firing within its potential pool or its receptive field, it will either activate or not, and decides whether it's going to be active based on how many of these overlap its connection, its connection space. That's where we were at before I started. And by the way, is anybody in here that doesn't know what they're looking at? Because I do have some. Feel free to use these chat commands if you want to learn the facts or links or whatever to other things. I added the chatbot. It doesn't do much yet, but one of these days it will. And just in case anybody cares to know, I've got 3 types of shows. AI chat, which is what we're doing right now, every Monday at 1. I've got work sessions that are technical engineering sessions, Tuesdays and Thursdays at 9. And then Fun Friday, which is whenever on Friday I'll do something fun. But check my Twitch schedule, or give me a follow if you want to get notified when I'm doing any of those things. It's all going to be related to AI in some way, because that's what I do. I work for Nementa as an open source community manager, and I try and make educational materials explaining this type of stuff to people who might be writing it in code. So you want to write some of this stuff in code, I'm here to help. Anyway, yeah, someday I want to integrate HTM into the tooling either for the chat server. I've got a server, Rhyolites Daemon, the chat bot Rhyolites Daemon. That's not just a chat bot, that's a server. So I'm going to hook him up to time series database, and we're going to start sucking up information from Twitch. And I already have an API to apply HTM anomaly detection over top of it. It's old, but I'm not sure if it works. But I don't know what I'm going to do yet, Mark. I'm still thinking it through. I honestly don't have time to do anything yet. I'm worried about NuPic. I'm worried about Python 3. I need to get that sorted out before I do any really fun stuff. So you're going to see me probably doing some boring technical Python work, trying to figure out how we're going to get a Python 3 environment for HTM, because our time is running out. The clock is ticking. I should put a countdown up here so it reminds me every day how many days I've got left before Python 2 is end of life. Anyway, if I had a yak shaving button, I'd push it right now, but I don't. So, trying to explain temporal memory. This is not an April Fool's joke. Hey, I think I recognize you, Sun123. I've been streaming on Twitch for like a month now. So yeah, like I said, Mark, I have no idea what I'm going to do. Definitely a time index. Everything's going to have time. I mean, ideally, no, we'll talk about that later. There's lots of things we could do, I think. Code thing to do keywords. I don't know what that means. Sorry. Okay, so a mini column activates in response to some activation in its input space. Thing to do in keywords like my channel button. I've got a lot of things to do like that. I've got a list of things to do to make the Twitch experience better. It's just getting to them. I came in over the weekend to do some of it. It's just busy right now. So I don't want to put too much of my time and effort into Twitch because I have a job. And honestly, this wasn't it before last month. So I still have to keep up with all my other responsibilities. And then this Python 3 thing is... Anyway, I'm not streaming to complain to you. Type something in and it does a time mark thing. Yeah, I did do that. Time mark right now. I just marked it. Or you can clip it, which is in the web UI. I don't know if this is what you're talking about, but with a keyword, yeah, there's a command to clip. I think it's \clip. Maybe. Nope, I don't know. But here's the clip button right here. Right there, if you've ever wanted to clip something. But anyway, I did figure out how to set a stream marker, so I did figure that out. Anyway, I'm getting off the topic. Let me get back to what I want to talk about on the whiteboard, which was temporal memory. Okay. So this mini column activates in response to an activation in its input space. And it, along with a whole bunch of other mini columns. You got to remember there are a bunch of mini columns. This thing is full of them, right? We're just looking at one. And each one of these has got all these cells, just like it. They're all over here, all right? Tons of cells. Now, in response to, like I said in the previous, when we were talking about this earlier, when we were talking about spatial pooling, if we get this input and there's been nothing is predicted, like we didn't predict this input, we're gonna burst the whole column, okay? And that means that this is new. This is one of the ways that this is how I like to explain it. There's two ways these cells fire. One is the mini column bursts, and the other is correct prediction. Okay, two ways that one of these cells fires. So let's say, I hate that. I got my black and my orange. You got your peanut butter and my, anyway. Guys, stop looking at my bald spot. I know it's sexy, but my eyes are right here. Okay, so let's say nothing is predicted, so we burst every column. I'm gonna get rid of this because I don't want to make my pen black. So we've got active cells, all the way down, active cells. Okay, so that's one reason one of these could fire. The other reason is there's another state that HTM neurons can be in, and we'll call that predictive. I'm gonna make it red, I guess. We'll make it red. Hey, in a beta. Okay, so let's say this cell is in a predictive state. What this means is that it has recently got enough distal input on one of its distal dendrites that an NDMA spike has just occurred, which is a dendritic spike. So you can Google dendritic spike, and there's a video I made about what a dendritic spike is if you want to see that. In fact, I'll do it for you because it's decent enough, and I don't want to go over it. Let me just show you. Dendritic spike Numenta, I think that's, and in videos, here it is. What is a dendritic spike? I'll link it.
What is a dendritic spike?
I don't want to. Sorry. I'm gonna pause. How do I mute this?
To other neurons.
Okay, that's me. My point being, usually, the soma spikes when it gets proximal input. That's what I'm trying to show there. If the soma gets proximal input, these are proximal dendrites near the cell body, then the soma fires. It creates an activation. But there's all these other dendrites that are around the edges that are distal, far away, right? If those get stimulation, it doesn't cause enough stimulation anywhere for anything to happen. And for a long time, we didn't know what they were even there for. But then we found out that this thing called an NDMA spike, which means if there's enough activity in one sort of localized area of a dendritic segment, that it would send a signal back to the soma, right? And it wouldn't be enough to cause the soma to fire. It wouldn't breach the activation threshold, but it would get it so close to the activation threshold that it only needed a little bit of stimulus to fire. So that's sort of a different state of the cell, and we call it a predictive state. If it gets enough distal dendritic activity, it can put it into a predictive state. There's not much more to this. And that's what I'm talking about here. If we have a cell that's in a predictive state, and I'll talk about where that distal input comes from in a minute, but right now I just want to tell you how it fires. So if it is in a predictive state inside this mini column, that means that this cell is predicting that this mini column is going to fire, or it's going to be activated in response to some signal coming through the input. So if that happens, and the activation of the mini column does occur, and there is a cell in a predictive state, that means it's going to fire fast. It's going to fire fast because it's sitting there waiting for proximal input. It just had some indication that it might be firing soon. It got real close to firing because of that NDMA spike. So if that occurs, then that means that prediction was correct. And it learns. So the synapses, or the permanences for its synapses, are then reinforced. That it thought it was going to be predictive. The NDMA spike put it into a predictive state. It actually was correct because it happened to be inside the mini column that the input space activated when spatial pooling occurred. And it was correct. So it gets reinforced. The distal connections that caused it to go into a predictive state can be reinforced to reinforce that pattern because it was something's coming. I don't know. Okay, that's ominous. I don't know what that means, but you're talking to the audience. Yeah. So where should I go? Where should I go next? The next. Now I have to talk about how does that cell get into a predictive state. That's the next logical thing. So that's sort of, I just talked about how a cell gets into it. It's looked at the distal connections. So each one of these cells in the mini column has distal connections. This one might be connected to that one, might be connected to this one. It could be connected to any cell in any one of these other columns, okay? This is the sequence memory. This is where this is gonna blow your mind. I think this is what BitKing was saying is coming. This is it. Once you get this will blow your mind. This cell has all of these different potential distal connections that might put it into a predictive state that represent one sequence. Now, this cell could also have these for many different sequences. So it could go into a predictive state because of some pattern that it sees evolving, or a different pattern that it sees evolving that's completely different. This cell can learn lots of different parts of patterns. That's just the way that memory sort of takes advantage of these sparse connections in your brain. Okay, let me take some questions. Are the distal SP connections in each cell connected to cells in other columns? Not in other macro columns, not in other cortical columns at this level. There are distal connections in other layers between cortical columns, yes, but not in this mechanism that I'm teaching right now. This is all happening within one layer of a cortical column. You don't have to go outside that layer at all. You can apply spatial pooling and temporal memory. It's like peanut butter and jelly. You got to have one for the other. Temporal memory works right on top of spatial pooling, and then we've got other mechanisms that can also work on top of temporal pooling in the same way, or spatial pooling in the same way. Okay, but we'll get into those at some point. Says the distal cell, oh, I guess so, yeah. So this neuron inhibits others in a mini column. The mini column inhibits other mini columns from expressing themselves. This neuron, I'm just talking about what's sort of happening inside the mini columns. So the inhibition I talked about in the last hour, that was when we were talking about spatial pooling. Inhibition happens when the mini column competition occurs. So we're sort of saying in the context of that competition, what are the cells within those mini columns doing? And they're learning sequence memory. They're learning the spatial patterns that are flowing through this space and connecting them over time. Okay, that's what these connections are. This guy is going into a predictive state because this cell was just on, that cell was just on, that cell was just on, and that represents something that it has seen before. It's last time it saw that, let's say, it fired next. That's why it's in a predictive state. And then if it turns out it's wrong, then we decrement those synapses so we have less of a chance of it being wrong in that way the next time. If it's right, we increment those synapses so we nail in that pattern. Okay, is the receptive field connected to the cells or the column? The mini column, I'm talking about so there's two different receptive fields here in this sort of idea. We've got the mini columns receptive field over the input space. That's what this and this is. This is the other receptive field. Every cell inside a mini column, every pyramidal neuron, also has a receptive field, a distal receptive field. This is the proximal receptive field, okay? That's the mini column is enforcing, and this is a distal receptive field of the same cell. Does that make sense? In what time frames is this happening? Okay, forget about time frames. There is no there's step after step. All you have to think about in the brain. This is a hard question. This is hard to understand, okay? But think about how time slows down when a traumatic event occurs, or when your adrenaline kicks in, how it feels like time slows down, and other times where time goes very fast. There's that idea of time being relative that I think is very applicable here, because all your brain knows is input after input, 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 input. That's it. This space just changes. How fast it's changing is sort of irrelevant. That's a context that might be expressed in the space, but as far as this layer is concerned, it's irrelevant. So it's a little hard concept to grasp, but let's see. Very short term. Yeah, very short term. Definitely. I mean, input after input. Really, really short term. Yeah. Let's see. The peak of each alpha brainwave. Sure. Sure, very fast. Continuous, absolutely continuous. Yeah, a more fair question would be the difference between n steps and the depth of them. I'm not sure what you mean by depth. Every step would be like a full sensory input, you know. Different regions of the brain are going to be processing portions of it, and they share their interpretations of space through at least through lateral connections across cortical columns in layer 2. That's a little further down the road. Okay. Is inhibition not only limited in time? Inhibition happens at every time step. Every time step, there's this mini column competition. Every input that lights up this board is a new competition that chooses the active columns in this layer, right? And then there's yet another computation, that is the temporal memory computation, that occurs within the space that the spatial pooler just created. It's the spatial pooler, the spatial pooling operation here is translating the semantics of this meaning into a new language of mini-column activations. And within that language of mini-columns, the temporal memory plays out. This temporal memory only works within the context of this space. Okay? Am I getting everything right here? Mark, correct me if I'm wrong, or in a beta, if you're still there. Oh, I think he left. Anyway, he talks about neuroscience stuff too. He's got some good presentations. Okay, great. Yeah. The world is not quantized. Quantized or quantized? Does that with brain waves to unify into time steps. Brain waves, yeah. Well, you think of it, I don't like, the neuroscience term is inhibition because this activation is essentially enforced by inhibitory cells. But I never thought of it, I never understood inhibition until I understood the neuroscience. What it really is a competition for which mini columns are active. When I did the stack rank thing, that's inhibition. That's it. It's inhibiting by saying I'm drawing a line here and I'm not letting any of the other mini columns express themselves. That's the inhibition part of it. But if you're confused about inhibition, you're probably overcomplicating it in your mind. It's really just the activation of mini columns based on stack ranking their overlaps with each of their inputs, and choosing only the ones that most strongly overlap that input to represent data, or to represent that input. So that's the inhibition part, and then the boosting sort of happens in addition to that. I didn't read a neuroscience paper. There's not necessarily a neuroscience paper that explains this. You'd have to read the neuron paper. That's the paper to read. Let me go back to our papers section. Why neurons have thousands of synapses. If that's definitely the paper you want to understand if you want to understand this idea of inhibition. And even in the BAMI, I read it again. Honestly, there is no shame in reading these. I had to read these several times, all of them. I feel like I'm a pretty smart guy, but I had to read these papers several times. So don't feel bad about it. It's like, I think it's normal. I think that's what you do when you do science. When you're faced with hard, challenging problems, sometimes you have to read things several times before they make sense. And sometimes I'll read something, completely discount it because I think, oh, that's not applicable at all. And then a year later, realize how insanely applicable it was. Anyway. So, all right, I was trying to explain temporal memory. I hope I'm still sort of on track. But I will I probably need to wrap up soon so I can get some things done before I have to go pick up my kids. So the tricky bit, so I talked about bursting and we talked about the distal connections and why this one is active. The tricky thing that I think that took me a while to understand with this also has to do with it being a high order memory. The inhibition timescale has a half-life effect in the basket and chandelier cell activations. Yeah, I can see that. I don't think we model that, but I can see that happening. I'm not sure how. I mean, that's one of those things. That's one of those questions. How strongly do you model these things? We could add like a whole procedure for adding that sort of half-life inhibition effect over each time step, instead of applying it, I think, every time step and not letting it move onward. That might increase the accuracy of things. It might, I don't know. I don't think that I know of we've ever tried that. There's a lot of things like that that could be tried within the realms of HTM theory that I'm talking about here. There's a lot of knobs that could still be installed and twiddled with, and maybe they'll have big effects and maybe not. This is like frontiers of science type stuff here. This is so Mark says it makes a big difference, and like I said, I don't think that we're modeling that at all. Anyway, it just shows you we're there's a lot of green field here. There's a lot of green field here for research, for whatever. So one last thing I want to try and explain is the tricky bit. Is high order memory versus single order memory. So if you understand like a Markov chain, this idea where I don't think I'll explain it, but basically you make your decision about what state you're going to be in as a unit dependent on the last time step. So it's the state of a system at the last time step. So you essentially are only looking at the last time step, or that's the only thing you have to make your decision. What this is something that's moving for even more than that. It's a higher order memory system. It can remember not only was this input a part of another input, but it also, there was one previous that I learned that it was a part of too, and that can be expressed in this layer of cells. And I really think the best place to understand that, and I'm going to go back to this again, is there's this one HTM school video. I worked a long time on these visualizations for this one, and I think it's still probably the best place to see how it works. And I'm just going to mute it and go. There's a point in here where you see the bursting happen, and you can see how the sequence just split. So I'm explaining these notes, and so I dialed in these notes in this little thing, and then had the sequence memory learn the system. No, I didn't want to do that. Don't do that. I pressed the wrong button. And I had the sequence memory learn this pattern of notes. And after a while, it learned it. It stopped bursting, because that's what it does. It bursts and bursts, and it's like, because everything's new. And eventually it stops bursting, and it nails it down. Every predicted cell is properly predicted, and everything's reinforced. All the weights are stable, and everything's locked in. And then if you go change one of the notes and watch what happens, that's the interesting thing. And so I'm going to leave this for you guys to do. If you want to do it, I'll share it at around, I don't know. I'm just gonna link it. Oh geez, I hate the time continue. I don't want to do that. I just want the there. I'm just gonna leave this for you guys to do, because this is sort of fascinating. I thought it was fascinating. So when I change the note, you'll see something happen that really nailed it in for me. So take a look at that if you want to understand it. Now I am going to log off. I got all you guys hooked in with me right now, but I've got some stuff to do. I really appreciate everybody hanging out. Before I go though, does anybody have any questions that they want me to ask, or any suggestions about how I could make this Twitch experience for you guys better or more interactive. If you come to my work sessions Tuesday and Thursday, I get real interactive with people. Well, I've been working on code with some people, looking at the same Trello boards and everything. So, yeah, thanks everybody for watching. I appreciate you jumping in and following me, etc. I'm not doing this to make money or anything on Twitch. This is really just to spread the information. You know, I want this technology to be free and open, transparent. Free as in speech. Transparent for anybody to understand it, no matter what company they work for or what where they are and the technological class, rank, whatever. Okay. All right. Let's do. Show me some backprop doing unsupervised one-shot memory. Thanks, Mark. That's true. All right, let's go find somebody to raid, because that's what we do at the end. It's always good to give away your, send off your viewers to someone else. Oh, I'm going to send it to this guy, because he was recently talking about him. So let's raid this guy. He is apparently, I think, doing a lot of algorithm stuff. So that's exciting. Let's do some, if you want to learn about algorithms, I was just explaining a couple algorithms to you just now, the spatial pooler, the temporal memory algorithms, etc. So we will go raid him when you guys are ready. Got 12 of us. Thanks for sticking through. 12 of us are ready to raid. I got 17 people watching right now. That's excellent. I really appreciate it. All right, we're ready to go. Let's do this. Take care. Everybody have a wonderful day.